So we started the recording for today's class. I'd like to start by solving some problems from this worksheet. We actually did see the theoretical questions of this worksheet earlier. Theoretical questions means these questions that ask you about the use, production, principles behind. They're a bit difference in wording for the set of questions, and I told you how to handle these differences. Before I jump into this whole thing, I'd like to set the premise for the class. সেটা হচ্ছে altogether আমাদের electromagnetism chapter electromagnetism না আরে ওকে altogether আমাদের remote sensing chapter এ ইকুয়েশন আছে হচ্ছে কয়েকটা আমি ইকুয়েশনগুলো লিখতেছি তোমরা দেখো একটা হচ্ছে incoming intensity is equal to reflected intensity plus transmitted intensity. Oh, transmitted intensity. To check number. Second equation হচ্ছে the ratio between reflected by original intensity is given by Z1 minus Z2 whole square divided by Z1 plus Z2 whole square, where Z equals to physical density of the object multiplied by speed of the wave through that medium. So if we use ultrasound, we use that wave. If we use X-ray, we use that wave, blah, blah, blah. Third, the attenuation that happens through a thickness of medium is given by the formula I equals to I naught e to the power minus mu naught লিখবো না কে লিখবো পি ছিল না কে ছিল কিসের জন্য আমাদের ভ্যারিয়েবলের নাম কি ছিল kx e to the power minus kx এখানে মনে রাখা জিনিস হচ্ছে যে for this equation to be applicable here, if we have a medium of thickness, let's say x, and k is the linear absorption coefficient, which is a constant, should be provided to us in the question. If the incoming wave, the amount of intensity that is entering in this wave from the very left side or from the very starting end of the medium thickness is I naught. As it travels through this medium, the amount that will be available at the very last end. This whole thing is happening within this medium. So I naught is also within the medium, I is also within the medium. So I naught is entering, I naught is available at the end. A pointer, last pointer, আমাদের available intensity হবে হচ্ছে I, which means there will be some reduction because of attenuation, because of spreading out of the energy and so on and so forth. So এই জিনিসটা এইটুকু হচ্ছে আমাদের ইকুয়েশনের বেসিক প্রেমিস. So let's go ahead and try to solve some mathematical problem regarding this one. আচ্ছা, let's have a look at this one. এখানে আমাদের কোশ্চেন বলছে an aluminum block is placed near to a small X-ray source of X-ray radiation as shown in figure 10.1. We have the X-ray source, so we have point A and B, aluminum block. X-rays from the source are detected at point A and B. State two reasons why the intensity of X-ray beam at point A is not as great as the intensity as point A. So B তে কেন আমাদের intensity কম? একটা হচ্ছে the way I think about it, A is close to the source, so the spreading effect is less. B is farther away from the source, so at B the waves are more spread out compared to A. This is one reason of attenuation, that farther you go from the source, the energy spreads out. The second reason is that because of the presence of the aluminum block, it absorbs a significant portion of the energy of the X-ray waves. That absorption absorbs up a significant portion of the energy from the aluminum block. So these are the two reasons that we're going to write over here in words, pretty basic stuff. Now comes a hypothetical scenario for human flesh. A cross-section through a model of a finger is shown in figure 10.2. So this is the finger. The thickness of the model is 2.4 centimeter, and that of the bone of the model is 1.1 centimeter. Parallel beams of X-rays are incident on the model in the directions AB and CD as shown in figure 10.2. data for the linear absorption coefficient, linear attenuation or absorption coefficient mu for the bone and the soft tissue in the model are given in figure 10.3. So we have the mu values over here. Bone has a higher absorption coefficient, 3.0 per centimeter, and soft tissue has 0.27 per centimeter. You can see over here that, that the mu is given in per centimeter, which means whenever you're gonna use the x value, the distance value, you have to use centimeters as well. Sometimes this can be given in per meter. In that case, you have to convert them into meter. If this is given into per millimeter, you have to convert this into millimeter, so that the units of these two quantity k and x, they should cancel out each other. Ultimately, you should have a single number, only a number, and as the power of the exponential sign. So this is pretty important. So keep your eyes open for this thing. Usually they don't do this mess up, but they have the opportunity or slash privilege to do this. So be careful about this thing. Now they say calculate the ratio of the intensity of the extra beam incident on the model divided by intensity of the extra beam emergent from the model for the beam AB and then for the beam CD. For the beam AB, it's pretty simple because it is going through a single piece of medium. So incident wave is I, and here comes this thing. Have a look. In this case, they are asking us to find out a ratio. Instead of the incident on the model divided by emergent from the model. So তার মানে হচ্ছে এই পার্টটুকু থেকে আমরা কি বুঝবো? Let me take out this image and try to select, copy. তো সবগুলা পিস করা। আচ্ছা, I'll need this one. Yes. Also need this one. All right. So zoomed out. আচ্ছা, এই জিনিসটা খেয়াল করো, আমাদের এখানে বের করতে বলছে রেশিও, কিসের রেশিও বের করতে বলছে? The question is asking us to find out the ratio of intensity of the extra beam incident on the model divided by intensity of the extra beam emergent from the model. So emergent intensity should be at the denominator side. The key equation that leads to this calculation looks like this: I equals to I naught e to the power minus kx. So we are asked to find out I naught by I. Emergent, so incident divided by emergent. So if we do I naught by I, this one goes at the bottom. So this one should go at the denominator. So this is equals to e to the power kx. This is supposed to be 1 by e to the power minus kx. So 1 by 2 ko na likhe, I'm sure e to the power kx ta likhchi. So now you start placing the values. For the beam AB, it's actually pretty simple because it is only going through the soft tissue, and the total thickness of the soft tissue is 2.4 centimeter, and the mu is 0.27. So you just place those values over here: E into 0.27 into 2.4. Now the value কত আসে? Help me out.
Sir, 1.91.
Someone else confirm this. ঠিক আছে?
Yes, sir, 1.91.
জি স্যার, ঠিক আছে।
All right. So এটা গেল। So this was pretty simple. এরপর সেকেন্ড কোশ্চেন আমাদেরকে বলছে, let's pick up the second question, যে for the beam CD, and CD ক্যালকুলেশন করার জন্য আমরা কিভাবে এই জিনিসটাকে হ্যান্ডেল করব? CD ক্যালকুলেশনটা অ্যাকচুয়ালি কঠিন না, but it's a bit intriguing. সেটা হচ্ছে, have a look. If you look for the beam for CD, it comes in through the comes in and enters the soft tissue, goes to a certain thickness. We don't know how much is this, but we will figure this out eventually. It goes a little bit thickness to the soft tissue, then it goes 1.1 centimeter thickness to the bone, and then it goes once again to this much thickness, and eventually it comes out over here. So we don't essentially know how much is this part or how much is this part. The question doesn't say this whole thing is symmetric either, but we can essentially understand the total length covered through the soft tissue is 2.4 minus 1.1. That is 1.3 centimeter. The beam CD covers a total of 1.3 centimeter of soft tissue and it covers a total of 1.1 centimeter through the bone. So both of these tissues will attribute towards the reduction of the factor. So in this, for this scenario, for beam CD, the equation is gonna be simply the multiple of two of these reduction factors. Two of these reduction factors means, let me try to understand, make sense to you. এই যে রেশিওটা এখানে দেখতেছি আমরা, this part of the ratio, this is basically a reduction factor. Reduction factor means that the emergent ray from a certain thickness of medium would be a certain portion of the original wave, original intensity. How much portion? This much portion. So if you have only presence of only one medium, you have only one of these variables. If you have presence of multiple mediums, you'll have multiple of these things multiplied with side by side. As a result, for the beam CD, this equation is going to be something like this. The emergent ray should be equals to I naught, which is the initial intensity or the incident intensity, e to the power minus kx, one for the CD part, let's say one for the bone part, and then once again e to the power minus kx. I'm reading the same format, just not to confuse you. And one should be used for, one portion should be used for the soft tissues, the other part should be used for the bone. So you have to use different values of k's and x's as obtainable from the figure and the table, and calculate the whole thing. So there is a so this, and if there were more of these things, I mean, let's say if inside the bone there was a blood clot which represented a third medium, you would have another values over here, and it could go on for a pretty good number depending on how many different medium this beam had to pass through. এই পার্টটা বুঝা গেছে কিনা বলো? Abiyaz, you are about to say something.
Sir, my question from before is answered, but this one, we're basically converting it into a single medium, right? Of a combined medium of soft tissue and bone, through which the ray passes, and we're accounting for.
Ultimately, the beam that will receive on the output side will be affected by the presence of both of the medium. We are not trying to consider both of them as a single medium per se. We are trying to find out the combined effect of the absorption of both the mediums together. So, or in other words, I can say that if we were to consider the two different mediums as a single medium, we would have to find out a combined mu value for both of them together, which we are not trying to do. We are simply trying to find out how much would be the reduction factor.
I understand, sir.
Beautiful. So try to do this and see how much you get. So for this thing, our equation is gonna be I equals to I naught by I. I'm only writing in this format because I want to use two different values, but I'm definitely not going to use same values. I'm just writing the expression of the equation over here. So don't confuse that this is going to be e to the power k square x square, because I'm not going to be using them as the same quantity, one for the soft tissue part and another for the bone part. If you really want, you can use 1, 1, 2, 2 if you want. I really don't bother for this because I'm going to replace these numbers right now. So here it's going to be, let's say if I go for the soft tissue part, my soft tissue is 0.27 and the thickness of the soft tissue for beam CD was 1.3 centimeter. So 0.27 into 1.3 multiplied by, now comes the bone. Bone has a linear absorption coefficient of 3.0 and the thickness of the bone tissue is 1.1. So 3.0 into 1.1. So এটা করে দেখো কত আসে।
$38.5, sir.
কত?
38.5.
Okay. Someone else confirm if this is all right.
জি স্যার ঠিক আছে।
All right.
ঠিক আছে স্যার।
Thank you. So that's basically how we do this thing. এই ক্যালকুলেশনের পার্টটা বুঝা গেছে কিনা সবাই দেখো একবার, take a good look at this whole calculation. If you have any question, you ask me about it.
মানে স্যার এখানে অ্যাকচুয়ালি মানে মিডিয়ামের উপর ডিপেন্ড করছে ইকুয়েশনটা কত বড় হবে, তাই না?
Perfect. Precisely. the bigger number of mediums that the beam has to pass through, the more of those e to the power kx factors will be coming as multiplied with the consecutively to the incident radiation. We have a see there was a usual answer in B science as to for a small X-ray image with good contrast may be obtained. Usual answers in B to suggest why for this model an X-ray image with good contrast may be obtained. Now, if you remember first, what does the word contrast means? The term contrast meant that the locations where it's supposed to be black are really black. Locations where it's supposed to be white are really white. The difference between dark portions and the bright portions are vivid. The brightness variations are large. That's what we mean by a good contrast. So you can see the question is asking us why this is supposed to give us a good contrast. If you have a look at the values over here, you can see that the X-ray beam that passes through the flesh only has a value of 1.91. An X-ray beam that passes through the bone part has a value of 38.5. So which means that the X-ray beam which is going to pass through the bone is going to be highly attenuated or highly absorbed. This X-ray beam will be absorbed by 38.5 times compared to what the original intensity was, where this will be only absorbed by 1.91 times of its original value. So you're going to have a really significant variation of remaining energy of the two output waves, which are going to come through two different pathways. So for AB, you're going to get a really dark image, and for CD, you're going to get a really white image, because the energy of CD will be really, really weak, because it will be attenuated by a very high amount. Just to make sure that we understand what this mark scheme says, we're going to have a look at the marks in this question number 7C. Let's have a look for this one. 7C. 7C and mark scheme therefore. Either much greater absorption in bone than in soft tissue, or I1 by I is much greater for bone than soft tissue. So that ratio that they are meaning over here, examiners report. Most candidates did not consider the two ratios when answering this part. Rather, they commented that the two values of mu without any consideration for the thickness or composition. So this is the important bit, that the mu is a characteristic property of the medium, but exclusively the mu does not attribute towards how much the beam would be absorbed. You have to understand that in this equation, both the mu or k, linear absorption coefficient, k and x, they are multiplied together. So together they produce a combined effect of the absorption. Exclusively the mu would not be a good enough reason. So this examination would say that most candidates did not consider the ratios, the true ratios when answering this part. Rather, they commented on the two values of mu without any consideration of the thickness or composition. So this is important. You need to appreciate that both of these factors, absorption coefficient, and also how thick is that material, both of these things provide us a good amount of information. This is that, and here we have another question over here. Distinguish between the sharpness and contrast in X-ray imaging. So you just give the differences of these two things. State two causes of loss of sharpness of an X-ray image. Data for the linear absorption coefficient of mu of X-ray photons are given in figure 10.1. We have two different values over here, bone and muscle. A parallel beam of X-ray is incident separately on a thickness of 3.5 centimeter of bone and on a muscle of thickness 8.0 centimeter. A parallel beam of X-ray is incident separately on a thickness of 3.5 centimeter of bone and on a muscle of thickness 8.0 centimeter. Calculate the ratio of these two things. Acha. In this case, they are asking us to calculate the intensity of the X-ray beam transmitted through bone divided by intensity of the X-ray beam transmitted through muscle. So they are asking us to find out the ratio of both of the transmitted intensity. So if we try to solve that, Well, MS Paint is not a very popular image for image editing or to be used as a whiteboard. That's why maybe they did not provide the what can I say, dynamic zoom over here. So it only goes by factor of 2. Anyway, we'll bear with it. তোমাদের অন্য কোনো টিচার কি MS Paint এ পড়ায়? Like any other teacher from any other source, coaching or school or anywhere else?
Not really, sir.
I'm the only one who.
They more or less use whiteboard. I guess.
Yeah, the whiteboard app is
Microsoft
really
whiteboard.
nice. The whiteboard app is really nice. আমি একদিন চেষ্টা করছিলাম and then I felt pretty good about this, then I came back to MS Paint. আচ্ছা আমরা এই জিনিসটা বের করি, intensity of the stream divided by, so we are trying to find out the ratio of two transmitted intensities. এখন transmitted intensity basic equation হবে কি রকম, let's say I through bone divided by I through muscle. এটা হবে হচ্ছে, the question says the up parallel beam, which means the incident beam would have the same initial intensity. So I naught would be same for both of them. I naught are exactly same for both of them. Into e to the power minus kx into e to the power minus kx. If you want, you can use mu as well. Using the term mu or k really will not matter for your mark scoring part. But the way your syllabus has designed that for X-rays, they have used the term mu, and for ultrasounds, they have used the term k. So if you use mu over here, yeah, you can. But since the question has given mu over here, it might be actually be a good idea to use mu over here so that the examiners don't feel confused about your conceptual level. The last thing you want to do is confuse the examiners. So it's just that simple. Then you start placing the value. I know cancels out. There is no botheration for this one. So you just place those values. E to the power minus প্রথমে হচ্ছে bone, that is 2.85 multiplied by বোনের thickness হচ্ছে 3.5 divided by e to the power minus 0.95 into muscle thickness হচ্ছে 8.0. দেখো এটা কত আসে,
Sir, 0.093.
আর digit এটা 2s হয়েছে আর এটা
0.
okay. Someone else confirm this, at least another person.
Yes, sir.
All right. So maths is actually difficult now, as long as you are acquainted with the equation and be careful to choose this thing properly. Well, so far we have done 2 questions for the transmitted equation. So here comes an example for the reflected part for the ultrasound. For X-ray, we don't have to bother about reflection because we don't take the reflected information anyhow. We only take that transmitted equation. But for ultrasound, reflected part and transmitted part, both are pretty important for us. I'll show you why. By reference to ultrasound waves, what is meant by acoustic impedance? You're just gonna write that basic definition in terms of the product of density and the speed of ultrasound in that medium. You can simply write that acoustic impedance comma z equals to rho into c, where rho equals to density of the medium, c equals to speed of ultrasound in that medium. That pretty much does the job. Write the equation, define the terms, move on. An ultrasound wave is incident on the boundary between 2 media. The acoustic impedances of the 2 media are Z1 and Z2 as illustrated in figure 10.1. So here comes incident wave, here is Z1, here is Z2. explain the importance of the difference between Z1 and Z2 for the transmission of ultrasound across the boundary. এই পার্টটা ভালো করে বুঝো। Explain the importance of the difference between Z1 and Z2 for the transmission of ultrasound across the boundary. What I need you to understand that if we have a look at this set of equation, the equation that I wrote first, that the reflected portion, it comes from this thing, and how much is reflected is this, and the remaining part gets transmitted. So if your reflected portion is pretty large, like really large, then the transmitted portion will be pretty small, and vice versa, because the sum of the reflected intensity and transmitted intensity will sum up to give you the original intensity or the incident intensity per se. So have a look. Here it comes Z1 minus Z2 whole square, and here it comes Z1 plus Z2 whole square. So important for you to understand that if we want to have a significant portion of transmitted portion, we would require this part to be pretty small. This part can only be pretty small if the numerator over here is quite small. The numerator over here can be quite small only if Z1 and Z2 are pretty close to each other. You have to understand that this ratio can never be bigger than 1, because on the numerator we have subtraction whole squared, on the denominator we have addition whole squared. So this ratio will always be, under all circumstances, this ratio will be less than 1. But how much big of a fraction are we going to get, or how much small of a fraction are we going to get, is dependent upon how close these two values are. If these two values are pretty close to each other, then that subtraction value will be really small. As a result, the reflected portion will be very small, and most of the wave can be able to transmit through. Vice versa, if the difference between Z1 and Z2 are pretty large, then you would have a much bigger subtraction result, and the fraction value would be significantly larger. So reflected portion will be much stronger, and transmitted portion will be somewhat smaller. So that's the significance of the values of Z1 and Z2 on the reflected wave or on the transmitted wave. So in this question, they are asking us that explain the importance of the difference between Z1 and Z2, difference between Z1 and Z2 for the transmission of the ultrasound across the boundary. So if I was writing this answer, this is a 3-mark question, I'd write the equation first. And then I would say that if the values of Z1 and Z2 are quite close to each other or quite similar, I'm not going to write same, because same would mean 0. If the values of Z1 and Z2 are quite similar, then the numerator is really small, and the whole fraction value becomes very small, which means reflected portion is really weak. So most incident wave intensity transmitted through the boundary, and vice versa. So I first write the equation and go ahead and use the equation for the explanation of what they're asking for us. That's how I would write the answer. But anyway, we'll have a look at the mark scheme to find out what the examiners look out for us. This question number 9B. Let's have a look. Have a look. If Z1 minus Z2 is small, mostly transmission. If Z1 minus Z2 is large, mostly reflection. So they have used both of the terms. I only said only one, so I'm going to lose 1 mark over here. If mostly not stated, allow 1 out of 2 marks for these first 2 marks, which means if someone does not write mostly, if someone only writes if Z1 minus Z2 is small, transmission, or if someone writes only transmission, if Z1 minus Z2 is large, only reflection, then they're going to lose 1 mark, because you can never have 100% transmission or 100% reflection if Z1 and Z2 are somewhat different. So mostly means is an important term for this explanation. Either reflection and transmission also depends on Z1 plus Z2, or intensity reflection coefficient equals to Z1 minus Z2 whole square divided by Z1 plus Z2 whole square. So writing of this equation scores you this 3rd mark, from which you should go ahead and write to this part. So they have given this mark last and these 2 logics first, but I would go the other way around. But now you know that you have to write for both of these expressions, that what would the small value imply and what would the large value imply. You better write both of these values individually. বুঝে গেছে? বলবান দেখো এই এক্সপ্রেশনটা বুঝে গেছে কিনা?
জি স্যার।
আচ্ছা, এরপর হচ্ছে ultrasound frequencies are as high as 10 megahertz are used in medical diagnosis. Say, state and explain and one advantage of the use of high frequency ultrasound compared with low frequency ultrasound. এটা মালা করছিলাম। High frequency ultrasound can be used to detect a very what can I say, very detailed view of extremely small parts or extremely small portions of image, or you can say that this gives us a much high definition ultrasound image or small pixel size. However you say, high frequency waves can help you detect small structures compared to low frequency waves for the same intensity. আচ্ছা, এখানে অ্যাকচুয়ালি ম্যাথটা ছিল না, আমি ম্যাথটা বাই করতে চাইছি এখানে। আচ্ছা, এখানে এই ফ্র্যাকশন রেশিও বের করতে, এগুলো বাই করবা। Be careful to look out for what is this ratio that they are giving. এখানে খেয়াল করো I by I naught, I by I naught রেশিওর ভ্যালু যা আসবে, I naught by ভ্যালু রেশিওর ভ্যালু উল্টা আসবে। So be careful to read carefully and replace the values carefully. That are you going to replace e to the power minus mu x, or are you going to replace e to the power mu x? মাইনাস সাইনটা হবে কি হবে না সেটা ঠিক মতন বুঝে তারপর প্লেস করবা। So read the question carefully, that which one goes on the numerator side, which one goes on the denominator side. It's pretty important. This is the one. Yes, this is the one. Let's have a very good look. Let's have a very good look for this question. Explain the main principles behind the use of ultrasound to obtain diagnostic information about internal body structure. We saw about this in an earlier class. So let's go for B directly. Data for the acoustic impedances and absorption attenuation coefficients of muscle and bone are given in figure 11.1. So we have muscle, bone, acoustic impedances are given in this part, absorption coefficients are given in this part. The intensity reflection coefficient is given by the expression. They have already also given us the formula, but in most cases this formula will not be provided to you, so you have to remember this formula. If you have seen that I always write this formula as z2 minus z1 whole square, z1 minus z2 whole square equals z1 plus z2 whole square, but in many cases they write it in this format. However you write, it basically means the same thing because the numerator is squared, so you are not going to be ever bothered by the minus sign. So as long as you write the thing properly, it just makes sense. Here comes the question. The attenuation of the ultrasound in muscle follows a similar relation to the attenuation of the X-ray in matter. A parallel beam of ultrasound of intensity I enters the surface of a layer of muscle of thickness 4.1 centimeter, as shown in figure 11.2. So I is entering here in the muscle. The ultrasound is reflected at the muscle bone boundary and returns to the surface of the muscle. So the wave is going to come in, reflect off, and then reflect back. So I want every one of you to speculate how the reduction will happen for this case, because we are now trying to deal with this thing. Okay, not enough space. So let's go to the next space. Okay. So this is the part that I really want you to appreciate. Have a look. The entering intensity is I. Let's say it is in I naught. It's I naught. Is this intensity, this amount of ultrasound is going to travel through a muscle thickness of 4.1 centimeter. So in this process of traveling, whenever this intensity, this ultrasound wave will reach to the bone boundary, it will not be as strong as I naught. Because of the thickness, there will be some reduction. We can calculate that reduction value by e to the power minus kx. So this is the first reduction factor. This x in this case is 4.1 centimeter. This is passing through this part. Now it falls onto this boundary, and now a portion of this incident wave is going to be reflected off from the muscle bone boundary. Now the ratio of IR by I is given by that thing, z1 minus z2 whole squared divided by z1 plus z2 whole squared. So if I just simply subject IR over here, how much fraction will be reflected exclusively, this would be this whole thing into I. So this is actually becoming the reduction factor for the reflected portion. So এখান থেকে যখন reflection হবে, when this wave is going to be reflected backwards, this much part will be reflected and the remaining will be passing through. For our question, we are trying to find out how much will be available at this boundary. So now the part that is coming back. If I try to give you a bit of a numerical value, if I try to give you a bit of numerical value, just to make sense with you, let's say here comes 100 intensity of energy entering into the muscle. In the passage through the muscle, let's say it reduces by 20. Then in the reflection boundary, let's say, so once it reduces by 20, the amount that is falling onto the surface is, let's say, 80. I'm just giving you some numerical value to give you a better understanding. Let's say out of this 80 amount of incident wave, let's say the reflects back is, let's say, 45. So when it will be reflected back, let's say in this reflection will happen in the same pathway. I'm just showing a different arrow size to make sure the numbers are differently distinguishable. So let's say the reflected amount is 45, which means out of this 40, 35 went in and 45 got reflected. This 45, as it will pass through the same amount of medium once again, this will once again undergo a reduction of 20, which means ultimately whenever it will come back over here, it will be detected right over here by the probe. The remaining intensity coming available at this point would be only 25. So here we're going to have 25 remaining out the whole ultrasound passage. So you're going to have 3 different reductions. Once it is passing from the muscle to the bone, once it is reflected, and once again as it is passing from the bone through the muscle in the reverse way. So here comes the first reduction factor, and then comes the second reduction factor, say Z1 minus Z2 divided by Z1 plus Z2. I'm giving a total whole square because it works. And then this same wave is going to go through the whole thing once again. So we're going to have this same e to the power minus kx once again. This is the total reduction value of the whole ultrasound traveling. So if you multiply this with the original intensity, you're going to get the final intensity that will be detected at this boundary by the ultrasound probe. So we have 3 reduction factors over here. Interesting for you, you should see that these 2 numbers are exactly same, because k in this case is the absorption coefficient of the muscle, x is also 4.1 centimeter. For this one, it is also 4.1 centimeter. So because these 2 values are exactly same, it is logical by mathematical operation to write this as I naught into e to the power minus kx whole squared. We can do this. Now,
Sir,
bullies.
2kx, na?
My bad.
Minus 2kx.
Bullies. Minus 2kx. I can actually write e to the power minus 2kx. Because in terms of the coefficient thing, it actually works. And this thing obviously multiplied by the whole ratio of the reflection factor. So Z1 minus Z2 whole squared divided by Z1 plus Z2 whole squared. That essentially comes over here, which is the reflection reduction. So এই জিনিসটা যে পসিবল এটুকু পর্যন্ত বুঝছো কিনা দেখো, এই ডিসকাশনটুকু বুঝা গেছে কিনা। Let me zoom out, take you a whole look and see if it makes sense. There will be 3 different reactions. এই ইনফরমেশনটা properly acceptable কিনা।
Sir, 90 degrees incident দেখে তাই 90 degrees আবার reflect হবে ওইভাবে আর কি।
We are considering that the whole reflection is happening in 90 degrees. For the sake of simplicity, we are not considering angles, because angle দিয়ে consider করলে আমাদের আরো কিছু information আসবে, but that's going to be difficult to deal with. I mean, we're going to have some angle variation over here. That is a more practical scenario, but for the sake of simplicity, এটা আমাদের সিলেবাসে দেওয়া হয় নাই। আর আরেকটা জিনিস হচ্ছে যে the waves which are actually reflected at some angle, they don't practically bounce back to the source, because whenever, if you think about the ultrasound probe, that rectangular device that we are rubbing on the patient's body to detect the ultrasound waves, the waves which go in a straight line and comes back in the exact same straight line, they are basically what is detected. Any wave that is reflecting at some angle, they're going to be reflected to some other locations. These are not going to come back to the ultrasound probe. So we can have the calculation, but they're not going to be detected by the ultrasound probe whenever they'll be reflected back. So we can as well consider them to be non-existent for our diagnosis. বুঝছো?
জি স্যার।
So এটা হচ্ছে এই পার্টের ডিসকাশন। আমরা এই ক্যালকুলেশনের পার্টটা একটু দেখি। প্রথমে বলছে হচ্ছে the ultrasound is reflected the muscle bone boundary and just the surface of the muscle, calculate the intensity reflection coefficient at the muscle bone boundary. So intensity reflection coefficient মানে হচ্ছে we have to calculate the Z1 minus Z2 divided by Z1 plus Z2 whole square. সো এটা এখান থেকে আমরা সিম্পলি রেশিও করে বাই করবো। দিস ইজ জাস্ট এ সিম্পল কোএফিশিয়েন্ট। অলরেডি ওরা ফর্মুলাটা দিয়েও দিছে এখানে, নরমালি পরীক্ষায় দেওয়ার না দেওয়ার পসিবিলিটি বেশি। So you just find this out. Then it says the fraction of the incident intensity that is transmitted from the surface of the muscle to the surface of the bone. The fraction of the incident intensity. Fraction of the incident intensity মানে হচ্ছে তোমার that is transmitted from the surface of the muscle to the surface of the bone. So in this case they are asking us এইখান থেকে এই পর্যন্ত যেতে কতটুকু fraction available থাকবে. So they are asking you to find out exclusively the e to the power kx. So this fraction essentially means they are asking, I mean, এই ফ্র্যাকশনটা যদি কবে বেস করি, let's it up over here. Okay, so this fraction that they're asking us right up here, this is basically the I divided by I naught for the transmitted wave, which would be e to the power equals to 3 to the power minus kx. So if they're asking us to calculate how much would be the reduction factor happening for the traveling. So here you're finding out the reflection factor. Here you're finding out the fraction for the traveling factor. You can find this out. এই দুটার ভ্যালু আমি মার্কস্কিন থেকে কপি মারতেছি because I really don't want to calculate them. কত নম্বর কোশ্চেন ছিল এটা? This was question number 13B. এটা হচ্ছে 0.33, এটা হচ্ছে 0.39. Then it says the intensity in terms of I that is received back at the surface of the muscle. এইখানে হচ্ছে ইন্টারেস্টিং ফ্যাক্টর, স্টুডেন্টরা এই পার্টটা বুঝতে অনেক সময় ঝামেলা করে। The part that will be received back at the surface, that portion in terms of I সেটা হবে হচ্ছে 0.39 squared into 0.33. 0.39 স্কয়ার কেন হচ্ছে এটা বুঝছো? বলবান 0.39 কেন স্কয়ার হয়েছে?
দুইবার ট্রাভেল করছে ওই সেম পাথটা দিয়ে।
Exactly. So that's the interesting bit. এই যে এখানে দেখো 0.33 into 0.39 square. It doesn't matter where you write this, place doesn't matter, but ultimately this has to be squared into I. Do not allow ECF from 1 and 2 if these answers are greater than 1. মানে হচ্ছে কোন স্টুডেন্টের এই ক্যালকুলেশনের ভ্যালু যদি আলটিমেটলি এই জায়গাতে এসে 1 এর থেকে বেশি হয় তাহলে তাদেরকে এই ভ্যালু ECF দিবে না, because students should understand by all means that the reflected and transmitted wave received in the behind the back to the probe can never be bigger than 1. I mean, you cannot get a bigger intensity than you have sent. So if someone gets this answer because of error and write up that answer as their final final presented answer, it means that they lack a significant amount of understanding for the idea of the process or for basic science, that idea of কি বলে যে কি যেন বলে conservation of energy law. That simple basic physics is not present in their head. So in those cases they would not be created for these things. It's unlikely, but some people might. Because if you wonder why some people might, because if somehow someone messes up this ratio, they're gonna get 1 point something, 0.3 যদি উল্টা করে লিখেন। If someone messes up this ratio without the minus sign, they're gonna get something more. So it is by all means it's quite possible that someone might come up with a number over here that is bigger than 1. But if someone represents that thing as a final answer, they're not going to be given any ECF values. So that's that. Example report দেখো।
Sorry, আগের যে derivation টা দেখাচ্ছেন ওটার মতনই।
হ্যাঁ, precisely. Again, there was many skills where this question was not attempted. In general, candidates who had completed parts 1 and 2 were able to complete this calculation successfully. So many students did not even attempt this thing, or many who did only multiplied these two numbers without the square, but this has to be squared because the wave is traveling back and forth twice. This is the part that I really wanted to discuss with you, because this is one of the parts that you have to understand, that the farther that the wave travels to the medium, the more times it will be affected by it, which should give you some pretty good understanding that how sensitive that detector should be. Because if you try to think about this figure, We are sending an ultrasound pulse from the left of the brain, let's say from the left of the skull. It is traveling through the skull boundary. Then it is traveling to the skull. Then it is traveling to the skull brain boundary. Then it's entering through the thick material of the left hemisphere of the brain. Then it's passing through the median fissure. Then it's passing through the right thing, and then it's going through the whole shebang that it underwent as it was entering on the right side as well. And then eventually all of them have to be reflected back through by penetrating through all of these medium once again. So these reflections that is detected on the ultrasound pulse over here had superbly low intensity. The device that is responsible to detect these last level of reflections this device has to be extremely sensitive towards detection. Otherwise, we would simply lose them. Do you understand the level of precision that we require for this detector to have to be successfully able to receive this thing? Can you appreciate the, what can I say? The sensitivity development of the scientist. I cannot come up with a better set of words, but I should. Do you understand how sensitive this probe has to be able to detect these things? Does it make sense? They're going to be, let's say, 1 millionth, 1 trillionth of parts in terms of the scent intensity, but this probe is assigned to detect those even small reflections. বুঝছো কি বলছে বলবান?
Yes, sir.
জি স্যার।
So that's that.
So Microsoft Paint page a derivation to the question variable.
Sure.
Thank you, sir. Sir, yes.
All right.
So স্যার 8 এর বিএ একটা কোয়েশ্চেন ছিল যে শার্পনেস অফ এক্সট্রা, এটা একটু ব্রিফলি মার্ক স্কিমের সেকেন্ড পয়েন্ট একটা এক্সপ্লেইন করতে পারবেন?
দেখছি আমি, দাঁড়াও। 8 এর বি।
জি স্যার, একটা কোয়েশ্চেন ছিল রিগার্ডিং দ্য শার্পনেস অফ এক্সট্রা।
আচ্ছা, distinguish between sharpness and contrast in X-ray images. Sharpness and contrast is state two causes for the loss of sharpness in X-ray images. So first of all, try to remember what sharpness was. Sharpness was the thin boundary between the dark portions and the white portions. The boundary or the transition between the sharp and bright and dark, that has to be very thin. So you have a dark region, boom comes the white region. There should not be a gradual decrease, or the penumbra should be really thin, or the mixed up region should be thin. That's the whole idea of sharpness, right? Or in other terms, I can say the borderline of the organs or the borderline of the tissues, bone or muscle or fat, those borderlines should be easily detectable. They should not be gradually diminished. That's the meaning of the sharpness. হ্যাঁ বলো কি বলছিলা?
আচ্ছা, মার্ক স্কিমে যে পেনাম্বরা পয়েন্টটা ছিল, সো দ্যাট মিন্স এটা তো যে ওভারল্যাপিং রিজনটা যেটা মাঝখানে থাকবে,
yes
পেনাম্বরা the higher the sharpness.
বলতেছি আমি, দাঁড়া ফিগারটা দেখাই এক মিনিট। মাঝখানে বলছে হচ্ছে scattering of photons in tissue use of colorimeter or no use of lead bead. So এগুলো ইউজ না করলে প্রবলেম হবে। Large penumbra on shadows, a large area of anode or wide beam, large pixel size. আচ্ছা, penumbra মানে হচ্ছে নরমালি, আচ্ছা আমি তোমাদেরকে একটা গুগল ইমেজ দেখাই। এটাতে একটা বুঝবা। Let's say we are having a eclipse. So this is the part where we have umbra, we have the full moon eclipse. So this is what it was the full eclipse. You're gonna have the sun altogether gone from sight. And these are the places, these shadow regions of the places are where you are going to see partial eclipse. So the sun will not be completely gone, but it will be partially blocked by the moon. So this is the region that's called penumbra, where you have some light available, but not complete light available. And this white region is where the day is still day. These people over here doesn't even know that an eclipse is happening. They have no clue. So এই পার্টটাকে বলা হচ্ছে penumbra. So we want this region to be as thin as possible, or preferably not present at all. বুঝছো?
Yes, sir.
আচ্ছা. Did you get your question answered completely, or do I need to go more?
Yes, sir. এখন বুঝছি.
Beautiful. So this was the extra question. And blah blah blah. Blah 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 blah. বাকি কোশ্চেন গুলো অ্যাকচুয়ালি তোমাদের নিজেদের ট্রাই করার পর আটকানোর পর আমি তোমাদের দেখালে ভালো হয়। So I'm not willing to actually go for some random solution for further questions, although I'm pretty much at the end of the worksheet. তোমরা বাকি কোশ্চেন গুলো নিজেরা ট্রাই করো at your convenience, and then eventually when you have some problem that you come across, then you can also ask me. Did any of you try some problem from the direct sensing worksheet that you would like me to discuss right now? Direct sensing worksheet থেকে কার কোনো প্রবলেম আছে? If you have tried, if you could manage some time to attempt those problems. If not, I'll start a discussion for the combination chapter. We still have 45 minutes. Combination chapter is pretty interesting, but it can be pretty disgusting at the same time, because there are certain weird stuff that you have to understand. আমি কি কম্বিনেশন পড়ানো শুরু করব? কেউ কি ডিসটেন্স থেকে প্রবলেম বলবা? এনিওয়ান?
No, sir.
People who attempted problems are not going to say it because they don't want to expose that they attempted the worksheet. People who did not attempt the worksheet are not going to say anything because they didn't want to do the worksheet. Good. Oh, Arnav has given us a problem. Beautiful. 24B and 24C. Arnav, thank you. We'll go for it. So, dear sensei, 24B. Here comes. Okay, question 24 দেখতেছি. This is from this worksheet. An electronic sensor may be represented by the block diagram of figure 9.1, blah 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 blah. B number বলছে, a student designs a sensing unit for the temperature change at 4-volt supply. A fixed resistor of resistance 2.5 kilo ohm and a thermistor are available. The thermistor has a resistance of 3.0 kilo ohm at 6 degrees Celsius and resistance of 1.8 kilo ohm at 20 degrees Celsius. Complete the circuit diagram of figure 9.2 to show how the resistor and the thermistor are connected to provide an output that is greater than 2 volt at 6 degrees Celsius and less than 2 volt at 20 degrees Celsius. Mark clearly the output V out. Okay. Let me think. Fixed resistor 2.5 kilo ohm and a thermistor are available. The thermistor has a resistance of 2.0 kilo ohm at 6 degrees Celsius and we want to have Actually, let me just step those things in series first. Let's say this is a fixed resistor of 2.5 kilo ohm. This is my thermistor. So this is gonna be my output, one of this thing. So when the question says that complete the figures happen to show the it should provide an output that is greater than 2 volt at 60 degrees Celsius. So at 60 degrees Celsius, the thermistor has a resistance of 3 kilo ohm, which is bigger than 2.5. So bigger than 2 volt should be available here. Okay, this is my P out. One of a circuit I'm explaining. Here we have the thermistor and the fixed resistor in series. I could have placed them anyway, but I just placed them in a random order that I personally like. Then I'm gonna judge them. The idea is at 6 degrees Celsius, the thermistor has a resistance of 3 kilo ohm. So the question tells me that the output is supposed to be greater than 2 volt at 6 degrees Celsius. The output is supposed to be greater than 2 volt at 6 degrees Celsius. So our total available voltage is 4 volt. This is 2.5 kilo ohm. If I want to get an output that is bigger than 2 volt, then I need a resistance bigger than 2.5 kilo ohm over here, so that the bigger fraction of the voltage is available across this one. So I can draw that out using a parallel connection. So whenever the thermistor has a resistance of 3.0 kilo ohm, which is at 6 degrees Celsius, this will make a voltage drop of more than 2 volt, because now this thermistor has a resistance bigger than the fixed resistor value. So V out will be now bigger than 2 volt, and vice versa for the higher temperature. Oh no, you had your microphone on for duration. You are saying something? Yes, bolo.
I understand.
বুঝা গেছে? আচ্ছা। এখানে ফার্দার বলছে suggest two uses of a relay as part of an output device. Suggest two uses of a relay as a part of an output. Suggest two uses of a relay. Okay. What does the relay can do as a part of an output device? One simple, I don't think this is related to this question. This is just a random question that is asking about the relay and output device. A relay can be useful to operate a high voltage circuit using a low voltage circuit. So you have a high powerful device that you have to operate by inputs, using inputs from a low voltage circuit. So you can use a relay over there. So you can sense the variables using a low voltage circuit, op amps and stuffs, and then you can convert that. And as for the second part, where else can we use a relay? I cannot think of a second use. Nope, I cannot. I'll look at the mark scheme. C. Remote switching. Switching large current by means of small current, alternating current from the high voltage to high voltage by means of small voltage current. Acha, remote switching is also a pretty interesting thing. Yeah. Remote switching মানে হচ্ছে, if you want to sense your variables, light or temperature or acoustic sounds or vibrations in one place and operate a device in a different place. So for example, let's say you want to sense the temperature inside in an industrial oven which is baking some breads or some buns or something like that, where you want to operate the heat supply by controlling the gas flow of the oven that should be in the inlet side of the oven. So the gas flow key or that pipe that is allowing the gas to burn in, that should be in one location, whereas you should take the temperature of the overall oven. So the sensing device and the executing location, they are not same. you can use a relay by extending out the wires of your low voltage circuit and bring up that magnetic coil in the location of the pipe where the key is located. So you can use remote switching for relay switches. বুঝছো কি বলছি? Simply by extending the wires, we can make it to work like a remote switch.
Sir, answer third example.
Third example. হ্যাঁ ইয়া বলো মুগ্ধ বলো।
স্যার আপনাকে একটা কোশ্চেন ইনবক্স করেছে, ওটার বিটা একটু দেখে দিলে ভালো হতো।
আচ্ছা দেখতেছি আমি। এখানে বলছে থার্ড এক্সাম্পল বলছে isolating circuit from high voltage. Isolating circuit from high voltage. Oh, this basically means that we are not মানে switching a high voltage by means of a small voltage and isolating circuit from high voltage basically is the same thing, which means that you are not going to run a high voltage connection through your op-amp circuits. You're going to run it by a small voltage individual sensing device where your main circuit is going to operate by a high voltage supply. So you're going to have completely different circuitry, one energizing the solenoid and parts, which is a small voltage circuit, and the high voltage circuit or the high power equipments, which are operated on a totally different circuit. You're not going to have any match up with these two circuits individually. Not going to be part of the same circuit. That's what it means by isolating.
Yes, sir.
Achha.
So, sir, can we ever control actuators using a relay?
This is a Jeep. Where is the Jeep? I don't see any animation here. Achha, maybe you crop that image as a Jeep. হ্যাঁ আচ্ছা বলো, হ্যাঁ রাফিদ কি বলছো বুঝি নাই, আরো বলো।
Sir, বলছিলাম যে can we ever control an actuator using a relay?
Yeah, definitely. Actuator basically means a type of switch which has a two state, on and off. So you can have, I mean, an actuator is basically a sweet name for a bistable circuit. Do you know what a bistable circuit is?
No, sir.
A bistable circuit is a switch that operates on two fixed condition, like 0 and 1 or 1 on and off. Simple example হচ্ছে মনে করো আমরা বাসা বাড়িতে যে সুইচগুলো ইউজ করি, if you press the on condition, it's going to be on till someone else, you or someone else physically makes it off. So it's going to remain in that on condition forever unless it is once again changed to off condition. So it has two specific output, on and off. This is what is called a bistable circuit, that if you get it a state, it's gonna maintain that state forever unless you physically change that state. This is one type of circuits that we talk about, and another type of circuit is those are called astable circuits. Astable circuits are those which operate on time intervals. For example, let's say any clock or time reading circuit that can flip automatically based upon a time information are called astable circuits. For example, an alarm. If you set up an alarm in your mobile device or any physical alarm device, after a certain time, it will automatically switch from off stage to on stage. বুঝছো কি বলছে?
Yes, sir.
Acha, let's copy this. Place it up here. A student designs an electronic sensor that is to be used to switch on lamp when the light intensity is low. Okay. Part of the circuit is showing figure 10.1. State the name of the component labeled in X for figure 10.1. Okay. What do you call that? LDR. You have to write the whole thing. Light dependent resistor.
শুধু এলডিএল লিখলে হবে না?
I would not prescribe this. কারণ typically যেখানে শুধু নামটা তোমার আনসার হয় সেখানে full name লিখতে হয়. Typically acronyms are not appreciated for this case. I'm not sure about the mark scheme, but I highly recommend that you write the full name. If the name itself is the mark scheme information, you should not use the acronym. You can use an acronym as a part of your large description. মনে করো তুমি ওই LDR ওয়ার্ডটাকে ইউজ করে তুমি একটা ফার্দার ডেসক্রিপশন লিখবা বা লজিক্যাল একটা সিকোয়েন্স লিখবা, ওখানে তুমি LDR লিখতে পারো, EMF লিখতে পারো, PD লিখতে পারো. But if those words it themselves are the masculine information, you should better write the whole thing. Electromotive force, potential difference, light dependent resistor, light emitting diode, the whole thing. On figure 10.1, draw the symbols for two resistors to compare the circuit for the sensing device. are related to computer cycle for the processing unit. Okay. Let's have a look. We want this to be on when the intensity is low. আচ্ছা আমি একটা করে আঁকতে থাকি ভুললে আবার মুছবো so we want this to be on when this this has to be turned on, so which means that we would require a switch that should look like this and a relay over here that should look like this. Relay, so আমি একটু একটা বক্সের মধ্যে দিলাম, বক্সটা না দিলেও সমস্যা নাই, just to convince the examiner that I know what a relay is. This is basically one of those back EMF things. আচ্ছা আইডিয়াটা হচ্ছে এই রিলেটা ম্যাগনেটাইজ হতে হলে কারেন্ট এদিক থেকে ফ্লো হতে হবে because there is a diode already influted over here, which means this output has to be negative. For this light to be on, this output has to be negative. এই আউটপুটটা যদি নেগেটিভ হইতে হয় তাহলে আমাদের ভি মাইনাসটা বড় হইতে হবে, তার থেকে বড় হইতে হবে, ভি প্লাস থেকে বড় হইতে হবে। Now the V plus value is definitely smaller than 5 volt because it is coming from the fraction value of the two resistors. So if V minus has to be big, we can simply connect the V minus with this 5 volt side because no, এটা ভুল হয়েছে, দাঁড়াও, hold up. When light intensity is low, then this one is consuming less voltage. So this one has a this one is consuming more than plus 2.5. So this one has a voltage less than plus 2.5. Okay, yeah. Makes sense. We just have to draw two equal resistors over here, R and R. And also we need this, and also we have to give the other এই ডায়োডের ডিরেকশনটা কোন দিকে হবে আমি ভুলে গেছি। I think it's going to be like this. আমি এই ডায়োডের ডিরেকশন একটু কনফিউজ, তার এই ডায়োডের ডিরেকশন একটু দেখে বলতেছি। মুগ্ধ, আমি আঁকা শেষ করলাম, তারপর আমি এক্সপ্লেইন করতেছি, ডোন্ট ওয়ারি।
Yes sir.
হ্যাঁ ঠিক আছে, yes. So I think this is all right. Now I'll go for the explanation. Try to understand. How did I start? I started from the endpoint and slowly work my way back because I preferred that way. But if we could very well start from here as well. The idea is a student designs an electronic sensor that is to be used to switch on a lamp when the light intensity is low. Part of the circuit is showing figure 10.1. So I want to turn on this lamp. So I drew a relay. This is my solenoid coil. This is the switch. And this rectangle thing represents the relay box. And because there is a diode over here, which means the current can only flow from ground to the left. So which means this solenoid can only be energized when this output is negative or lower voltage than the ground connection. This is ground. That's why I gave a minus sign over here for my personal reference, which means current can only flow upwards. Now, for this to happen, the output of the op-amp has to be negative. And output of the op-amp negative hoy kokhon. You should remember that V out is given by gain multiplied by V plus minus V minus. এই হচ্ছে বেসিক ইকুয়েশন, ঠিক আছে? তো আউটপুট নেগেটিভ হইতে হলে আমাদের V plus less than V minus হতে হবে, so that the subtraction gives us a negative value, so we get a negative V out. So if we want to get a negative V out, our V plus should be less than V minus. এখন কোশ্চেন বলছে হচ্ছে when the light intensity is low. When the light intensity is low, then this resistance should be large. This resistance being large means from the 5-volt whole supply, this will consume more than 2.5 volt. That's what I'm assuming. It will consume the bigger portion of the available voltage. So the voltage of this point should be less than plus 2.5. So voltage of this point at when this is low, voltage of this point is less than plus 2.5 volt. A part 2 বুঝছি কিনা দেখো আগে।
Yes, sir.
Yes, sir. So if this is less than plus 2.4, which means all that I need to make sure that in this condition that the V minus has to be exactly plus 2.5, because that will be my tipping point, that will be my feed voltage. So in this case, V minus is my fixed voltage, which is an 8 উপর based on V plus কে control করতেছে or compare করতেছে. This is basically a comparator circuit. You can see there is no feedback over here, so it's essentially a comparator circuit. So I had to provide the V minus a fixed 2.5 volt supply. That's why I use 2 equal resistors and a single junction from the 2.5 resistor over here. That means that a pointer voltage সবসময় কি হবে? Plus 2.5 volt fixed থাকবে. So whenever this condition is achieved, there will be an negative output. Current will be flowing up to here. There will be relay switch. This is the diode that is making sure that it is only going to be energized for the negative supply. Then for the protection of back EMF thing, I'm connecting this diode over here. The reason I looked it up because I forgot the direction, and the reason I was happy because you can see this description or this set of circuit was given when this op-amp output was positive. So op-amp output যদি পজিটিভ হয় তাহলে আমাদের ডায়োড হতে হবে হচ্ছে এরকম, সেক্ষেত্রে আমাদের ডায়োড 2 বা ব্যাক ইএমএফ ডায়োডটা হতে হবে আপওয়ার্ডস। So if this is negative, then both of them reverse the direction. So এই ডায়োডটা অলরেডি আমার একে দেওয়া আছে, এই ডায়োডটা হচ্ছে এই ডায়োডটা, other than in this branch they are due over here. So this other diode should be reversed. So this diode was upwards, this diode has to be downwards. That's why I was very happy about to find it out that yes, what I presumed was correct. This must should do this properly. এখানে কি আমাদেরকে লেবেল করতে বলছে, লেবেল করতে বলে নাই। So I should not bother for labeling. তোমার এই ভোল্টেজ চলগুলো লেখা লাগবে না, জাস্ট আর গুলো দেখাইতে হবে। এই আর দুটাকে ইকুয়াল রেজিস্ট্যান্স এটা তোমার দেখাইতে হবে so that the examiner is convinced. I think that's pretty much it, I believe.
স্যার ব্যাক ইএমএফ এর জন্য যে আরেকটা ডায়োড দেওয়া হয়েছে, মানে এই অল্টারনেট পাথ দিয়ে কারেন্ট মানে ফ্লো করবে যখন মানে the current is harmful for the op-amp.
Yes. Or
Okay, sir.
more
Thank you,
precisely,
sir.
when the op-amp switches its output for a small duration at that instant.
Yes, sir. Thank you, sir. বুঝেছি, sir.
Beautiful. Anything else, anyone?
স্যার
From the upper
9C1 এর ডায়াগ্রামটা একটু দেখাতে পারবেন?
Sure. Figure pattern shows the second diagram, second coupling and ideal op-amp, ideal operation for op-amp. So we have V1, V2, 9 plus standfold, V out. The voltages applied to the inverting and non-inverting inputs of V1 and V2 respectively state the values of the output voltage V out. This is nice. এটা তো আমরা করছিলাম মনে হয়।
এটা করেছি স্যার।
স্যার আমার ডায়াগ্রামটা লাগতো।
ডায়াগ্রাম কই? আচ্ছা এই সি এর ডায়াগ্রাম?
জি স্যার।
আচ্ছা sorry. I misheard you. My bad. The input voltage Vn is in B is provided by a sensor circuit. Complete figure 8.4 to show the sensor circuit that will provide a voltage that is increases as the temperature of the sensor increases. Acha. So let's try to understand the question first. This is a fixed supply that we have. আচ্ছা আমি এটা বের করে নেই, এখানে দেখতে পারবো না। All right. So complete figure of 8.4 to show a sensor circuit that will provide a voltage output that increases as the temperature of the sensor decreases. So we want to design a circuit that output will increase as the sensor temperature decreases. So clearly the output connection. So basically we'll need a thermistor, temperature sensing resistor, and a fixed resistor, and use it as a potential level circuit. So I'm just placing them in random positions. Up or down doesn't matter because I'm gonna choose my position of the V out logically afterwards. So first time let's say I'm এটা হচ্ছে আমার fixed resistor, এটা হচ্ছে আমার thermistor. So I'm just gonna write R over here. আর না লিখলে কোনো সমস্যা না, I'm just writing this because I want to. Now এটা হচ্ছে আমার একটা আউটপুট পয়েন্ট হবে। এখন আমার V out either এখানে হবে অথবা এখানে হবে। কোনখানে হবে সেটা আমি জাজ করব। বুঝছি কি বলছি? And দেখো, when the temperature will increase, this one will undergo less voltage, less resistance. Less resistance means it will now have lower voltage consumption, so more voltage will be available over here. So আমাকে কোশ্চেন বলছে show a sensor that will provide a voltage output that increases as the temperature of the sensor decreases. So এটা টেম্পারেচার বাড়লে হাই ভোল্টেজ হবে এখানে, তাহলে লো ভোল্টেজ হবে এখানে। আমার টেম্পারেচার যদি কমে যায়, so if the temperature decreases, now let's try the other thing. If the temperature of the environment decreases, then this one will have a larger resistance, and if this one has a larger resistance, this one will consume a bigger fraction of the voltage from the supply because this is a potential level circuit. So more voltage will be available across its parallel combination. So basically this should be my V out, where I should get bigger voltage as the temperature drops. That's basically it. বুঝছো কিনা দেখো।
স্যার এই পার্ট অফ সার্কিট কি ফিগার 8.2 এর সাথে অ্যাড হবে?
আচ্ছা, এই পার্টটাকে আমাদের ফিগার 8.2 এর সাথে অ্যাড করতে বলে নাই। এখানে ওরা যেটা বলছে যে ইনপুট ভোল্টেজ ইন Vn is provided by sensor circuit, মানে হচ্ছে আমাদের দেখা দিচ্ছি আমি অ্যাকচুয়ালি এখানে আমাদের যে ভিনটা যে আসতেছিল না, এই যে ভিনটা যে আসতেছিল, এই ভিনটা কোত্থেকে আসছিল সেটা একটা পসিবল লোকেশন বলছে। তার মানে হচ্ছে আমাদের এখানে এটাতে জাস্ট ভি আউট হিসেবে আমি লেবেল করলাম, বাট সার্কিট হিসেবে এইখান থেকে যে আউটপুটটা বের হবে এটাই হচ্ছে আমাদের ওই সার্কিটের জন্য ভিন। এখান থেকে আমাদের ভিনটা ভাগ হয়ে ফার্দার সার্কিটটা ড্র হয়েছে, মানে হচ্ছে এই সার্কিটটা ড্র হয়েছে। So this part is coming out from a potential divider on the left like that.
স্যার এখানে ভি মাইনাসটা ফিক্স থাকতেছে, আমরা ভি প্লাসটা জাস্ট দেখতেছি এই সার্কিটের মাধ্যমে।
হ্যাঁ, এই সার্কিটে ডেফিনেটলি yes এই সার্কিটে ভি প্লাসটা হচ্ছে ভ্যারিয়েবল, ভি মাইনাসটা হচ্ছে ফিক্সড ভ্যালুস। ইয়েস,
ডায়াগ্রামটা একটু আরেকবার দেখতে পারি?
শিওর। ডায়াগ্রামটার লজিকটা বুঝো। ডায়াগ্রামটা you cannot memorize this, but you have to understand the logic. লজিকটা বুঝে গেছে কিনা, নাহলে আমি আবার বুঝাই। I can.
স্যার একটু আবার বুঝাবেন, বুঝিনি।
তুমি এই পার্টটা খেয়াল করো। ফার্স্ট অফ অল হচ্ছে if we want to get a variable voltage output, we need a potential level circuit. Potential level circuit ক্রিয়েট করার জন্য আমাদের আগে টেম্পারেচার সেন্সিং একটা রেজিস্টার লাগবে, which is a thermistor, the symbol for thermistor, আর একটা ফিক্সড রেজিস্টার লাগবে, এটা হচ্ছে ফিক্সড রেজিস্টার। ফিক্সড রেজিস্টার 8টা না লিখলেও হয়তো, আমি জাস্ট এটা এমনি লিখছি, এটা লেখার দরকার ছিল না। সো এই দুটা এখন আমি যদি এখান থেকে আমি যদি বেসিক একটা আউটপুট বের করি, আমার পসিবল, আচ্ছা আমি এক্সট্রা পার্টগুলো মুছে ফেলি, আমার পসিবল দুইটা আউটপুট লোকেশন হতে পারে। একটা হচ্ছে এখান থেকে আমি আউটপুট নিতে পারি, অথবা এখান থেকে আউটপুট নিতে পারি। দিস ইজ দ্য টু অপোজিট টাইপ অফ আউটপুটস দ্যাট আই এম গোনা গেট। একটা টেম্পারেচার সাথে বাড়বে, আর একটা টেম্পারেচার বাড়লে কমবে, এন্ড ভাইস ভার্সা। সো হুইচ ওয়ান ইজ আই এম গোনা লেবেল অ্যাজ মাই ভি আউট, দ্যাটস হোয়াট আই এম ট্রাইং টু ডিসাইড রাইট নাও। এইটুকু পর্যন্ত কনস্ট্রাকশন হচ্ছে বেসিক। যদি এটা আমার এলডিআর ডিপেন্ডেন্ট হতো, আমি এখানে একটা এলডিআর রাখতাম। এটা যদি আমার ভাইব্রেশন রিলেটেড হতো, এখানে পিজোইলেক্ট্রিক ক্রিস্টাল রাখতাম, ব্লা ব্লা ব্লা। সো এখন আমি জাজ করবো যে এখানে আমি কোন পাশটাকে which side of these two output side I'm going to choose as my V out. That's what I'm trying to choose here. What it shows that provide a voltage output that increases as the temperature of the sensor decreases. As the temperature of the sensor decreases. Now try to understand that when the temperature of the sensor decreases, এটার temperature যখন কমে যাবে, when this will decrease, this will start to have a higher resistance. Having a higher resistance means, in terms of ratio, this resistor will now consume a bigger fraction of the voltage from the fixed supply. ঠিক না?
Yes, sir.
It means whenever this will have a bigger fraction of the voltage, the parallel connection out of this part will also provide a bigger output voltage. Now my question says that we want to find out a voltage output that increases as the sensor temperature decreases. So essentially এই পার্টটাতে আমাদের voltage increase হচ্ছে. So I'm going to label this as V out. That's basically it.
বুঝছি স্যার, থ্যাংক ইউ।
Sure.
স্যার 4B1 টা একটু দেখাতে পারবেন?
Okay. Let's have a look. Question was হচ্ছে the circuit diagram for P1 1 is an amplifier circuit incorporating an operation amplifier op-amp. On Figure 9.1, mark with the letter X the virtual earth. Explain what is meant by virtual earth. Acha. In bright sunlight, the light dependent resistor has a resistance of 200 ohm. Calculate for the area in bright sunlight the voltmeter reading. So when bright sunlight is falling over here, what is the voltmeter reading? Acha. So this voltmeter reading should be the output. In this case, acha. Output calculate করার আগে আমি gain calculate করি কারণ হচ্ছে আমার তো এটা হচ্ছে আমার inverting amplifier. So gain equals to হচ্ছে minus RF by R in. এখানে feedback resistance হচ্ছে কতটুকু 4.2 কিলো আর আমার ইনপুট রেজিস্ট্যান্স হচ্ছে the series combination of both of these সেটা হচ্ছে 200 plus 1000 এটা মাইনাস বসবে এটা হিসাব করলে কত হয় দেখো তো 4200 divided by 1200 minus 3.5. So once we get the gain, the remaining part is pretty simple. So এখানে আমাদের output হবে হচ্ছে V out equals to gain into V in. এখানে দেখো আমাদের input voltage source টা উল্টা দেওয়া আছে. So I'm going to write gain over here হচ্ছে minus 3.5. Input voltage হচ্ছে minus 1.5. Together we're going to get 5.25 volts. Positive. So you can choose to write the plus sign or you can choose not to. Before I write this value as my answer, I have to look at the supply. Before I write my final answer, I have to look at the supply. Supply is plus minus 9 volts. My output is plus minus 5.25 within the range. So this is going to be my output. যদি এটা না হতো তাহলে আমাদের লিমিটিং ভ্যালু গুলাই হতো। এটাতে প্রবলেম ছিল নাকি এটাতে প্রবলেম ছিল?
জি স্যার B1 এ প্রবলেম ছিল, বুঝছি।
ঠিক আছে, beautiful. Anything else, anyone? No, আচ্ছা ঠিক আছে। We have a little bit of time, so I'll just start the application chapter so that we can jumpstart in the next class. So we'll do the soft start today. All right, let's close everything else. clear page 100% zoom. First of all, this figure shows us that there are three different ways of communication. We talked about this in our very first class of the application booklet chapter, that what are the different things that we have in our chapter. This is direct communication, this is wired communication. This is by two wires. We have a microphone, solenoid current, and speaker making the sound. This is usually what we call an analog channel, where you use direct voltage input for transmitted over wires. Analog channels can also use digital data, which can be very useful over short distances, but not so useful over long distances. For really long distances, we preferably use this one. We talk into a microphone, which uses some amplifier. This trident thing is basically the circuit symbol for an antenna or an aerial. Both of the words are equally acceptable for the name of the symbol. So the aerial sends out the signal, the loudspeaker receives this aerial over here, receiving antenna receives it, amplifies it, demodulates it. It does a lot of things over here. I mean, a lot of things happens over here, a lot of things happens over here as well, and eventually it goes over here. In this chapter, we are gonna see in very simplistic terms, like super simplistic terms, in a largely generalized version, or very trouble-free version, very basic part of what essentially happens here and what essentially happens here. So we're gonna see some stops that happens right at this location and at this location. So we're gonna see about that. We have some stops over here. I would like you to read these stops, and this is pretty simple. Okay, we can read it right now. Sound can be transmitted either by directly as in A, or via the alternating currents induced in a moving coil microphone and received by a moving coil speaker as illustrated in B. It is also possible to communicate using radio waves by simply amplifying the audio signal and applying it to a suitable aerial as illustrated in C. However, there are two fundamental problems with this system. Only one radio station can operate in the region because the wave from a second operating station would interfere with the first. The aerial required to transmit frequencies within the audio range 20 Hz to 20 kHz would be both very long and if inefficient. The radio waves would not travel very far unless huge powers were used. So if we simply use the audio frequency of our voice, which basically falls within the radio frequency, because radio waves basically is the very last range of our of the defined electromagnetic spectrum. So no matter how small of a wave that you think about, it can be considered as a radio wave. So if we do use our voice signal frequencies, which is 20 Hz to 20,000 Hz, the typical audible range for human beings, and use that exact frequency for radio signal transmission, we require extremely high amplitude of those signals for it to be able to cover large distances, because the frequency is very low. So the intensity proportional to frequency squared, we're not getting any benefit from that aspect, because the frequency being very low means the transmitted signal itself will be very weak. It will be really, really weak. It cannot be powerful. And that's one thing. And the other thing is that as the signal will travel further, it will definitely undergo attenuation, spread out. It will decrease in its signal strength. Intensity will decrease. So if we want the signal to be transmitted over large distances, the initial signal strength has to be significantly strong, so that it can actually be detectable over large distances as well. To achieve this, we can only have this if we prefer to use the frequency of the human audible range, 20 Hz to 20,000 Hz. We have to essentially use an aerial. We have to use the transmission process with extremely high power. In this case, high power means using really high amplitudes of the intensity wave, I proportional to amplitude square. We have to go for that. And using very large power apparently might not sound very troublesome, because it's only two words. Large power, what's the big deal? But operating with large power comes with a lot of problems. High resistance, high heating effect, high loss within the source system. If there is some noise in the signal, the whole noise also gets amplified by a large amount. So using really large power amplifiers has its built-in problems alongside itself. We're going to see about those things some of those things later on in the chapter as well. Nothing from you people. So I'm gonna close them. Then comes this part. Both these problems are solved by the process of modulation, the principle of which is illustrated in figure 3.2. In modulation, a high frequency wave known as the carrier wave has either its amplitude or its frequency altered by the information signal in order to carry the information. এই ডেফিনিশনটা খুব ভালো করে পড়ো, এটা আসে। What is modulation? The principle of which is illustrated in figure 3.2. In modulation, a high frequency wave known as the carrier wave has either its amplitude or its frequency altered by the information signal in order to carry the information. What it essentially means, something like this. You have an information signal to transfer from one place to another place. That information signal itself does not have enough power / energy to be transmitted over long distances. To be able to enable it to travel over long distances, you want to merge this information signal with a carrier signal of really high frequency. Having high frequency makes it more powerful. Having it allows it to contain more energy, more intensity. So you're going to merge these two things in a way, in a logical way, so that the combined thing can travel much farther. So you can transmit the signal much farther distance. That process of combination is called modulation. And there can be two types of modulation. One is called amplitude modulation, and one is called frequency modulation. We're going to change either of this property in this modulation process, never both of them simultaneously. Very important. We're only going to do either, I'm going to do either amplitude modulation or we're going to do frequency modulation. Before I even start to talk about this, you have these notes with you, so you can have a look at your notes as well. Just look at these 4 graphs and try to understand what is happening. The one thing that I will tell you that this is an unmodulated carrier wave, and this is the information signal that you're trying to send. This is a unrealistic information signal, but this is a very simple one. This is basic sine curve, or you can consider this as a single note of frequency, like or p or tang, like that. Like there's no quality. There's just a pure sine wave. So we want to somehow merge these two to become one. There are 2 different ways you can do this. Amplitude modulation gives you this thing. Frequency modulation gives you this thing. Before I tell you anything, I want you guys to look at this and try to gather some ideas. I'll give you some time. Okay. So what do you see? You essentially do understand. You should be able to understand what is being altered. There are a couple of things that I'd like to take your attention to. Mind this information. What you can see, whenever we're gonna merge these two, unmodulated carrier signal with the information signal, in the process of amplitude modulation, in no case the amplitude of the modulated signal becomes 0. You can see when the information signal reaches the trough, the very lowest point, the amplitude of the modulated signal is the lowest, but not 0. When the information signal is at its crest, here or here, the amplitude of the modulated signal is highest. So depending upon the amplitude variation of the information signal, depending on the amplitude modulation of the information signal, the modulated wave changes its amplitude, but never to 0, which means what I need you to understand, let me just crop this picture. What I want you to understand that whatever the amount of variation of information signal that we have from here through here, I mean, this amount of information signal variation, well, in this case it says diffusion over time. In terms of digital signal, I mean, diffusion over time is basically a very crude variation of signal, something that you can see in the CRO. But if you want to understand it in terms of the actual signal that we get from the piezoelectric crystals, typically this displacement is given in voltage. It's voltage versus time. So if you talk into a piezoelectric crystal, or if you have a microphone, which is basically a piezoelectric crystal, and you place a tuning fork in front of the piezoelectric crystal, that tuning fork will register a voltage variation like this. Like without the vibration, there'll be 0 voltage. When there is compression, it's going to have some positive voltage. Whenever it's under rarefaction, it's going to give us some negative voltage. So that's why I'm writing the term voltage over here. So what I want you to understand that over this amount of time, the voltage of the information signal will vary from this positive value to this negative value. In the modulated signal, this same information will be translated into, from this part, if I go vertically down, not the very perfect of the drawn down through, but bear with me. This amount of variation of voltage of the information signal is represented by this amount of amplitude change within the modulated signal. This is never becoming 0, important bit. But this thing is changing from positive to negative. So let's say if this is, let's say, plus 10 volt to minus 10 volt, where this signal might as well be, let's say over here it is, let's say, plus 12 volt, and this lowest value, let's say, plus 5 volt. So the variation is 7 volts. So you are having a total of plus 10 to minus 10 variation in the information signal, represented by a variation of 12 volt to 5 volt variation. So, or to be more precise, only a 7 volt variation. So a total of 20 volt variation in the information signal, it is represented by a magnitude of 7 volt variation on the information signal. So there is a ratio like this. There is a inherent property like this that controls the variation. This is one thing that I want you to understand. These values that I'm trying to show you over here are assumed values. These are random, figure not drawn to scale. These are not realistic values, but I'm trying to give you some idea that that's how it works. This is one part. And one beautiful thing is that the frequency of this information signal is perfectly represented on the modulated signal as well. How? If you have a look over here, here you have a high amplitude for the information signal. Here you have another high amplitude for the information signal. If you consider the gap between them, this is actually one time period. You'll see in the modulated signal, from maximum amplitude to minimum amplitude, and once again to maximum amplitude, this variation will also have the same amount of time period, which means each similar amplitude orientation gives you the time period of the information signal. So if this information signal, let's say, had a frequency of, let's say, 100 hertz, if this information signal has a frequency of 100 hertz, then this amplitude modulated wave will also have maximum amplitudes 100 times every second. So you'll have these peaks showing up 100 times within 1 second of time duration. So whatever the frequency of the information signal is also perfectly reflected in the modulated signal as well, but with some appropriate scale. This is one thing. And everything that I just said over here, so this is the part that I wanted to understand to begin with for the amplitude modulation. What happens in the frequency modulation is just the same thing, but here we're handling the amplitude information. Here we're going to handle the frequency information, but we're going to keep the amplitude same. You can see that this amplitude is pretty much the same as the original. Now, but you might as well see that here the unmodulated carrier had an amplitude of this much. Visibly, this is bigger than that. So did we increase the amplitude? We can. By simply using an amplifier, we can. But ideally speaking, the frequency modulation will not bother with the amplitude variation. The total amplitude may be bigger or smaller, but there would not be any variation of the amplitude. That's the bottom line. Frequency is being changed over here. So what you can see over here, that whenever the information signal had a zero intensity, let me use blue for this one maybe. Whenever the information signal was zero, we had some frequency to begin with, and this frequency is the same frequency as the original carrier. As the voltage of the information signal goes higher, this frequency is increasing. You can see that the waves are getting collapsed, they are getting shrinked, they're getting squeezed, and you have the most squeezed scenario at this point where the peak of the information signal is. Have a look. Here the wave is the highest amount of squeezed, and then as the signal wave goes down, this thing comes down, and eventually at this point, the frequency of the modulated carrier would be exactly same as this one. So if this original carrier has a frequency of, let's say, 1000 hertz, I'm using 1000 hertz because I assume this one to be 100 hertz. This is supposed to be very, significantly larger compared to this one because it has to carry a lot of amount of energy. That's why I'm choosing this to be 1000 hertz. So over here, at this location, this will be 1000 hertz. At this location also, this will be 1000 hertz because the signal is zero. This would be something higher. Now, how much higher? That also is defined by some scale. For example, here, I assume that this was plus 10 volt. If we assume that this frequency modulation has an increase of, let's say, 12 hertz per volt increase. Let's assume this thing. Let's say this frequency modulation is going to work by a scale of 12 hertz per volt. What does this mean? This means for each individual voltage increase of the information voltage of the information signal, you're going to have a change of 12 hertz of the frequency modulated wave. So what this means that when the information signal will rise from 0 to 10, you're going to have a total of 120 hertz of frequency increase, which means at this location, your frequency is exactly 1000 hertz, as same as this value, and at this location, precisely at this location, the frequency would be 1000 plus 120, that is 1120 hertz. This will reduce to 1000 1 second over here, and whenever this thing is minus 10, this will also work with this same scale, 12 hertz per volt, but now this will be reduced by 12 hertz for every volt. So now the information signal has a value of minus 10 volt. So at this location, the frequency of the signal will be 1000 minus 120 hertz. So that should be, I think, 880 hertz. So at this location, your frequency of the signal, modulated signal, should be 8080 hertz. So it will work by a certain parameter by which you can define at which location how much frequency are we going to have. এই ডিসকাশনটুকু বুঝা গেছে কিনা that there is a method to this madness. It's defined. It's not random.
Sir, frequency modulation kind of like.
আরেকবার বলো, বুঝি নাই, আরেকবার বলো। ফ্রিকোয়েন্সি
আমি বলবো?
হ্যাঁ বলো, আমি কোশ্চেনটা বলো, আমি কোশ্চেনটা বুঝি নাই।
Frequency modulation, is it like compression or rarefaction?
I wouldn't say compression and rarefaction because we have compressions and rarefactions throughout. I'd say increased compressions and rarefactions, if that works better. But in a controlled manner. That's very important.
The Principle is the same, like correspond to compressions, and troughs correspond to rarefactions, like the spreading out and collapsing in of the waves.
Yeah, but if you think about this, that if we are saying this as a, let's say, actual physical longitudinal sound wave, we have compressions and rarefactions, but we have close compressions and rarefactions over here, and we have less close compressions and rarefactions over here. So that's the difference. That's what makes the information stand out. Mukto, bolo.
Okay,
স্যার এম মডুলেশনের জিনিসটা কি হচ্ছে আমি বুঝিনি। আপনি বলেছেন যে it will never be zero, but the signal is clearly touching the axis, মানে এটা বুঝলাম না।
Oh, no. What I'm saying is that the amplitude of the signal will never be zero. Displacement of the signal can always be zero. It is for every single cycle, it is reaching zero every once in a while. It is reaching zero every once in a while. The displacement of the wave can be zero, but the amplitude, maximum displacement, that will never be zero. Because if the amplitude becomes zero, that means that the signal has finished. The signal will always be there. It will never be, what I'm meaning is that it will never look up like this. Let's say that direction and then it becomes flat. এরকম কখনো হবে না।
আর স্যার কিন্তু মানে নেগেটিভ ভোল্টেজও তো আছে, এখন শুধু +12 টু +5 কেন ধরলাম?
ওইটাই বলতেছি যে আমরা পজিটিভ ইনপুট ভোল্টেজের পজিটিভ ভ্যালু থেকে ইনফরমেশন সিগন্যালের পজিটিভ ভ্যালু থেকে ইনফরমেশন সিগন্যালের নেগেটিভ ভোল্টেজ পর্যন্ত যে ভ্যারিয়েশনটা, সেটা মডুলেটেড সিগন্যালের ভোল্টেজের একটা সার্টেন অ্যামাউন্ট অফ চেঞ্জ হিসেবে দেখাবো, so that this thing will never become perfectly zero. Let's say over here, let's say this voltage was, did I define this voltage? No. Let's say this voltage was maybe 7 volt. Not 7 volt. Let's say this voltage was initially 8 volt. So let's say over here we have 8 volts. Let's assume. So when it is 10 volts, then it, let's say, becomes 12 volt, and whenever it is minus 10 volt, then it becomes +5 volt. Actually 8 volt actually ঠিক হলো না। 12 আর 5 এর মাঝখানে কত হয়? What is the mean value of 12 and 5? 17?
8.5 sir.
8.5. So let's say this is 8.5. ঠিক আছে? So whenever the information signal goes up from 0 volt to 10 volt, then you are having an increase of 8.5 through 12, that is let's say 4.5, 3.5 volts. Where you are having a 3.5 volt increase in the information signal amplitude for an in the modulated signal amplitude for an information signal amplitude variation of 10 volt. And then as it decreases from that 10 volt to 0, and then once again from 0 to minus 10 volt, you're having a total decrease all the way up to +5 volt. But this total variation of from +10 to -10 will never cause the modulated signal to reduce to 0, something like this. This will never happen. That's what I meant. It will become small, but amplitude will never be 0. The signal will still be there, but with a smaller amplitude.
স্যার এখানে কি কোনো ফর্মুলা ইউজ করতে হবে নাকি মানে র্যান্ডম ভ্যালুস নিয়ে ডিল করব আমরা?
না আলটিমেটলি আমরা যখন ম্যাথস করব তখন আমাদের এখানে নেসেসারি ইনফরমেশন, নেসেসারি ফর্মুলা এগুলো আসবে, বাট আমি ওই ফর্মুলাগুলো এখন তোমাদের দেখাচ্ছি না, বা হচ্ছে ইনফরমেশনগুলো স্পেসিফিকলি বলি নাই। I was trying to give you an idea that how this conversion works.
Yes sir, এখন বুঝেছি স্যার। থ্যাংক ইউ স্যার।
Sure, no problem. এই পর্যন্ত বুঝে গেছে সবার? ফার্দার কোনো কোশ্চেন? আমি ক্লাস ক্লোজ করে দিব, বাট ইফ I really wanted to make sure that this part is understood well. Anyone else?
Sir.
Yes.
For amplitude modulation, if you trace the peaks of the amplitude modulated wave, will it form a similar waveform to the informational signal?
Similar, but not same. That wave will have the same frequency as the information signal, but not essentially the same amplitude.
Okay, sir.
All right, kids, thank you very much. আজকের জন্য এটুকু থাক, আর আমি লেকচারগুলো একটু পরে আপলোড করে দিচ্ছি। বাই।
Bye, sir.